let's first understand what we are actually meaning when we are talking about big data. Big data has got actually two things that you need to keep in mind when you're talking about big data. People usually tend to say that what is big data? Big data is a large chunk of data that cannot be fit, in maybe in one system where been clustering and a lot of things they'll go into. But the point that is missing over there is that, of course, it's a large chunk of data. There's no second thought on that. The second thing is that it is unstructured. Of course, big data is large, and that is why it is big, and it is unstructured. So now, first let's understand that what we actually mean by unstructured data and why the management of unstructured data required us to coin a new term and then make a new technology, make new tools and all those things. So data can be divided into two parts, of course. So if we are talking about unstructured, the other one, the counterpart is structured data. So now what is a structured data? Structured data, you cannot just say that structured data is something that you can just put in a structure. That's on a surface level. But if we want to dive deep a little bit inside that, a structured data is a data that can be stored in the database by following the RDBMS theory. RDBMS means a relational database management system. So we are trying to form a database management system, means a particular system that helps us manage the data, which are relational in nature. The relational data means a relational database can hold relational data, as simple as that. But what is a relational data? A relational data means that's a data about some entities, and entities, by entities I mean programmatic representation of real life objects. That is what an entity is. I'll just give you an example. Anyway, so let me just finish the statement I'm writing. So data about some entities that have some sort of relation among them. The entities should have some sort of relation among them, not the data. So entities that have some sort of relation among them. As like what can be a real life example? Say for example, you're trying to build maybe an ERP application, or maybe let's talk about a CRM application where you got a lot of clients' data and a client base, huge databases going on. Now, if you talk about a CRM, it starts with one single client, right? It starts with one single client identified by client ID. Some sort of client ID. Either we are giving the ID, we are asking them to choose the ID. Our system is automatically providing an ID, but something like that, client ID. This is in fact called a unique key, not really a primary. A unique key can be a primary key, a foreign key, whatever that might be. So client ID is the unique key that, and it completely depends on the person who is actually generating and designing the database structure. So I say, for example, me being a DBA, maybe I am a DBA, just imagine like that, and I'm saying that client ID is my unique key. I have not yet decided whether it is primary or not, and that is neither required for our current scope of discussion. So now in this CRM, everything revolves around the client. What kind of things can revolve around the client? Number one, the details of the client. Number two, it can be, what should I say? The payments that are related to the client, maybe payments coming in, payments inflow, payments outflow. There might be some kind of those promises. These things can be involved. Let's talk a very simple CRM kind of a thing. So details of the client, if we are talking about, we are talking about his email ID, basically contact information, email, phone number, whatever that is. So contact information. After they're talking about his maybe a full address, his complete name or something, whatever else you want to put over there. But here is one thing also, that is client ID. That is also. And now let's talk about the payments inflow. When we are talking about payments inflow, let's talk about the same client ID we are talking about and the amount, maybe the date on which the money is coming, and maybe if there is some installments also going on, something like that, installment dates, right? And say let's talk about outflow. That also involves the client date. So let's just keep it short and let's talk about the first two parts. So this client ID is the unique key that is actually making the relationship between these two things work together. Now, what are the entities over here? The client is over here, and here the institution is there, right? The institution that is taking the money. So that is the relationship between the entities that is being set up over here, and that is being taken care by this, I should say, the relational data that we have, and we are placing it in a kind of a table format and all those things. So this is called a structured data, because how many ever clients you have that you can just map in this particular structure. The problem comes in unstructured data is that you cannot find a generalized way of treating the data. When this is a situation, what do you do? Of course, this is something called unstructured data. So what do you do in this case? Well, there are a lot of things you can do with the data. Now, the first point we need to keep in mind when we are talking about doing something with the data is what is our end objective that we are trying to achieve, and what all things that we have right now with us. So it comes like this. So you've got a lot of data. You're trying to form some kind of a black box kind of thing that will take you to your end objective. So this black box is the problem that you're trying to solve. Now this black box contains multiple components. Components means what? It contains something like, of course, a lot of computers. So computing powers, you can say. And when you talk about computing powers, of course, we are talking about, it is called algorithms, which comes under the softwares. The softwares will be the thing that will be implementing those algorithms. So now when we talk about algorithms, what have we got in algorithms? Well, we have got a lot of algorithms. Like if you know about Hadoop, there is a very famous algorithm called Mapreduce. So let's understand how we are dealing with this part, the first one, the computing powers part. So for dealing with computing powers, we have got two separate ways of, you should say, designing the computing resources that you have got. So number one happens to be centralized computing pattern. And the second one is, of course, decentralized. So when you talk about centralized computing pattern, we are talking about a structure where we have a hub. It is called a hub set up over here. And after that, we have got some nodes going on. And these nodes will be connected in a direct connection with the central hub, but they will not be having their own individual connections with each other. So this is the connection we are trying to set up. So you've got hubs and nodes. When you have got a lot of unstructured data with yourself and you are trying to take that lot of data to its end objective, you need to trigger several, you can say, algorithms of yours, which will actually take you to the end objective. Now, either that, see, the structure, overall structure stays the same in centralized or decentralized. The difference comes that whether you are operating at a node or you are operating at a hub. So when you are operating from a node on a hub, that is called a centralized computing pattern. So you will be having separate nodes. They are actually working on building these algorithms, and you have all the data stored in a large chunk of database, not a database, a hard disk you can say, because that will be mostly in format of a CSV or maybe something like that. So that is sitting somewhere. This is your hard disk, you can say, and that is getting connected to your particular hub. And your hub is actually doing a two-way communication with the HDD. Means it is fetching and writing data to and from the HDD. You are telling what to do. The instructions are given from the node. So this hub is a fairly powerful computer. And these nodes are smaller computers. They are actually generating the algorithms and they are doing a little bit of local testing. So this data, for example, there is maybe we are trying to solve out a problem where we are trying to figure out which horse will win in a horse race. So you've got 10 million data with yourself. So that can be of that particular horse that has run in several tracks. That can be of different horses running in the same tracks, and a kind of a mixture of this. That depends on our real life problem. So you will be having some separate copies of that particular data, a subset. Okay. So that can be, for example, let's say just 1K data you have with yourself in a node, and you are running a small test on this particular subset. I mean, I'm talking about how the things are actually designed from the industry perspective. You have a subset of the same kind of data, and this subset is also chosen in a particular way so that the samples are kind of matching with each other the way it should be. Right. So that is falling under the data engineering part. Anyway, so we are pulling out these samples like that. So we are talking about this subset and we are operating on this particular subset to get an idea whether or not our algorithm will be working properly. There are several parameters that we have to set, like for the thresholds. So what all threshold you should keep, what all standard deviations will be coming out of your computation, right? And for example, means and all these things. So depending upon all this, you have to choose your subset. Now, from this subset, you are actually running your test, and then you are throwing your test on the hub. This hub has got something called a scheduler. The scheduler will be taking, every node on a round robin fashion or on whatever particular algorithm they are giving. So there is something called HRU algorithm, LRU algorithm, a lot of algorithms in there. And let's understand in a round robin fashion. Node 1, node 2, node 3, node 4, node 5. So like that, the schedulers will be taking up the algorithms that are sent from the node to the hub, and then it will just apply it on the data set that is present in the hard disk, this big data set. And then we are actually talking about the big data part. Understood the theory, right?
Can you like tell like scheduler ka thing one more time if it's okay?
Okay, fine. I'll just show you a diagram. You'll understand. I'll just make a diagram. So let's say a time curve, you can say. Okay, a time basically. Time is going in this direction. So now at time say t0 or something, we are starting. These are the 4 unit times. It can be minute, second, microsecond, nanosecond, whatever it is. So we are taking 4 time intervals starting from 0 to 4, total 5 time points. So now when our scheduler is running, we are starting at time 0, t0. We are reading from node 0. And in this interval, we are processing the data, processing this algorithm with that data. Okay, that 10 million amount of data. Now, definitely you cannot process 10 million data just at the given period of time. That is not going to happen. It is going to take a huge amount of time. Exactly. I mean, when we talk about Mapreduce and all those things, that takes a lot amount of time. Right. So that depends on the data set you have got and the way it is, the SDB and all this and so on. So it will work on that particular data set for a given amount of time, then it will move to node 1 algorithm. So when I say node 0, I mean the algorithm sent by node 0. Algorithm sent by node 1 and like that, node 2, node 3. So for example, you have got only 3 nodes. So 0, 1 and then it comes to node 2. After that again it goes to N0. Again it goes to N1 and like that it keeps on going. Okay. So this is what a round robin fashion looks like if you are using a round robin scheduler. So you have got your chunk of data. So it will be making, say for example, 3 nodes you have got. So it will be making 3 different copies of the particular data. And it will be keeping it separately for each of the algorithms. Right. So it is giving the individual copy, but the scheduler makes sure that it is giving equal time to every algorithm to be processed. And why is this equal time required? Because it also takes into account time complexity of the algorithm. So you will know that which node is first finishing. Because see, there is no consideration of space complexity when you are talking about algorithms that work on big data. Because space complexity you cannot keep, the space is going to be used, and that is going to be a large amount of data, gigabytes and terabytes of data. But we are only concerned about time complexity and of course accuracy. Now, when we say accuracy, we do not say 100% correct result because that is not possible. So when we talk about accuracy, we are talking about as much as we can reach, giving there is something called assertion. Assertion means what we are actually determining manually. I mean, when we look at the data and we analyze, like for example, you have got a statistician in your team. They are doing the statistical parts and all those things. So they will be preparing an assertion data, and you will be mapping on top of that. All these things are done automation. Nobody actually manually sits and does that thing. So on this assertion based result, you will be checking out your actual versus expected. So the far similarity you are getting, I mean the closest you are, the better your algorithm is. So we are talking about assertion, the accuracy part, and we are also talking about the time complexity part. If some algorithm is giving me an accuracy of, say for example, 81%, and the time complexity turns out to be, let's just talk about time instead of going to time complexity, because that is once again in the algorithm designing part. So that is a separate part we shall talk about later. So if you're talking about the time part, say for example, it takes 1 hour to complete the task. 1 hour is a very less amount of time, giving a terabytes of data, but still, let's say it is taking 1 hour, another one is taking 1 hour 15 minutes. But the 1 hour 15 minutes is giving me an accuracy of 90%, where the 1 hour wala is giving me an accuracy of say 63%. So I shall still go with the 1 hour 15 minutes part. But if it is like, if the 1 hour is giving me 89% and 1 hour 15 minutes is giving me 89.5%, I'll stick to the 1 hour. So it's you can say kind of a manual decision which one you want to stick to, and of course you can automate the things also. Got the point, right? How it is happening. So this is the centralized computing pattern, and this is how the thing works out. Now let's talk about decentralized computing pattern. We have our local hard disks that are present with the nodes. So there is a two-way communication channel that is set up between a node and its corresponding hard disk, and similar for the other two also. I'm not drawing it. Say we have got a large chunk of data, and once again that 10 million data, something like that. Now these hard disks are capable enough to store that amount of data. So what we're doing is that, see, this is also a hard disk. My algorithms are being prepared on the hub. My algorithms are being prepared on the hub and there is no scheduler. And the same copy of data is kept in all the hard disks. Same copy of data is kept in all the hard disks. So there is data redundancy because we want to keep data redundancy. That is what we want. And that is one big thing that differentiates between a relational database model and unstructured data. The main idea behind data redundancy is that we want the data to be available. See, two things. Number one is available locally. And number two is that if one particular node goes down, you have a backup of the data somewhere else. HDFS works on this model. I'll come to HDFS in a moment. So we've got this 10 million data everywhere. So now what our hub is doing, it is basically connecting. I mean, it is basically has all the algorithms. You are making the algorithms, uploading it to hub. Maybe this hub you do not have with yourself, so you are using some kind of a client FTP application that is pushing the things to the hub, something like that, and then you're running on production script, which is basically running this thing, pushing them to the node and running them. That is the idea. Okay. So somehow you have your algorithms being thrown to the node, and that node is processing this thing. So now what does thing do? This thing, now this particular fashion that we had in the scheduler model, this one, that was still kind of parallel, but using the same computation power. This is kind of parallel what I'm saying, because it clearly looks like a serial way, doing this, once again this. But the clock runs so fast that you will get a kind of an idea of a parallel processing. And practically there is no difference between parallel processing and this kind of a serial processing. So we are completely getting rid of this thing, and we are actually involving each individual individual computation power for performing each individual algorithm running task. That is the idea. So you are involving the hub only to take care about what you want to push, where you want to push those decision making abilities, and the hub will not be this big. I mean, by big I mean this powerful, because it is not doing that much amount of task. It has got two different tasks actually. Number one is algorithm management, and number two is network management. So what comes in algo management, I already told you, pushing the correct algorithm in the correct thing in the correct time and all those things. And network management again constitutes of two things. Number one being that you're trying to constantly monitor the connections. So you're trying to monitor the connections with constant listeners, custom listeners. And the second thing is that you make sure that you are providing support in case of downtime. And what I mean by providing support, that just doing some kind of a load balancing, and not load balancing, like pulling up a DR, environment, something like that, where you have all your data redundant data kept. So you can just push the data from that node to another node. Say, for example, these last two nodes, node number. So in case of node number 3 and 4, you want to keep them inactive. In case 1, 2, or 3, someone goes down, we'll just pull up these two nodes, any one of them, as a replaceable node. So they will be, considered as a TRs. They also have their local hard disks with the copy of the exact data. So that is the second thing that comes under network management. So hub is just doing this much amount of part, and you are connected to the hub from your local machine by using some kind of a FTP. So now this technology, this centralized computing pattern, that was very much evolving when big data actually just started to come into the market, before even Hadoop was there. And then Hadoop was once again an Apache release that changed the entire concept by completely reversing the way it is doing it. Because the problem you face in scheduler pattern thing is that, the centralized pattern is that you don't have redundant data. These subsets, the data scientists used to do like this. They will be pulling out the center subsets in a way so that when you do a union of the subsets, you get the original data set back. But that is not really a very intelligent way of doing the thing, because geographically these nodes will be present anywhere in the world. So that is not a very intelligent way of doing. And if one node goes down, you have a backup node. Now that also has, you have to say that, for example, I want this node to be backup of node number 2. So that will be having the exact set of data that node number 2 has. Otherwise, the algorithm and the union pattern matching, all these things will not work out. So that is the challenge, but they used to do like that till Hadoop came into the market and it gave birth to the decentralized model. So now what happens in this decentralized model? You have already seen that. How does Hadoop use this particular thing? So now Hadoop does not really go and copy this 10 million data everywhere. So in Hadoop management, we are dividing the data in multiple chunks. We are dividing the entire data in multiple chunks. Somewhat like this, but not exactly. This multiple chunk division is not done in any particular, intelligent way or something like that. It is not done like that. It is simply divided into bytes, 128 bytes, for example. So we are just trying to divide the data in 128 bytes. So, for example, you have got 1 kilobyte of data, and you're trying to break them in 128 bytes blocks. So it will start like, for example, 128 bytes, the first ones, second one, third one, fourth one, it is going on like that. And maybe at a particular point of time, you realize that you do not really need 128 bytes of data. And you can just, do with a even lesser amount of data. 128 bytes is taken because 128 bytes is basically, it is 2 to the power 9, right? Sorry, 2 to the 7. 2 to the power 7 is 128 bytes. So it is taken in that particular format because it has to be taken in the 2 format, because of course binary bytes we are talking about. So definitely 10, it has to be in the base of 2. And it is taking the 2 to the power 7 because in the market search, Hadoop team found out that that is the lowest chunk of data. If the largest chunk of data, if they go, then they will be having the least amount of extra memory wastage. They'll be having the least amount of extra memory. What do I mean by that? I mean by that is that, say, for example, you have a data and you're making some blocks out of this, like this, one block, and then there comes your second block, and there comes the third block. So now the third block is definitely a smaller one, as you can see. So say this is x bytes of data, this is x bytes of data, and this is y bytes of data. This total are 2x plus y bytes of data, and you're trying to break your entire data in x bytes, x bytes. So this last y bytes, you still have to take a segment of x bytes only. I mean, you actually will be wasting some memory because you have to pull out an x bytes, but this particular part will be a wastage. So this part will be a wastage, right? This part. So that we can solve this problem, so Hadoop came out with this 128 bytes concept, right? It is breaking into 128 bytes of chunk, and it is saying that that will give you the least amount of extra page wastage and all those things. So what happens is that, so it will be taking this amount, and it will be taking this amount and making two different segments out of that. Let's call it segment 1 and segment 2. That we have got this particular two segments of data with ourselves, and then what we are doing, we are placing these two segments in two different physical hard drives. Now HDD1 has segment 1, as you have already understood, and HDD2 has segment 2. Now think about this particular model. This model, the decentralized model. Okay. So this is our segment 1 lying over here. And here we have our segment 2. And we are pushing in the same algorithm on segment 1 and segment 2. We are not going for different algorithms. We are pushing in the same algorithm on segment 1 and segment 2. Now, these hard disks also are broken in multiple parts. Understand this thing properly. These hard disks, we are taking each of these hard disks, they are broken into multiple parts. So you have got 5 nodes together. Okay. So you have got your segment 1, that is for node 1, let's say, lying over here. And you have your segment 2 lying over here. Seg 3 over here. And seg 4 over here. Right. And you have 5, 6, total 6 nodes you have got. So these segments are kept in hard disk 1, that is present with node 1. Now, when node 1 is operating, it is operating only on segment 1 and not on segment 2, 3, and 4. Node 2 is operating only on segment 2 and not on the other ones. Node 3 is operating. So in this way, what we are doing, now see, if you have got 6 nodes, and if you have got 4 partitions in your hard disk of each node, then what happens is that you are basically ending up copying one segment more than once, isn't it? Because you have total got 6 segments, but 24 partitions. 24 partitions you have got, and you have got total 6 nodes. Now each node will be actively working on only one segment. So 6 segments are there, and 24 partitions are there. So definitely now one will be taken off. So you can just say 3, 6, 18. 18 partitions are there. 18 partitions are left for performing the data redundancy task. So we can directly go and we can put the data inside that, isn't it? Yeah, so that helps us in doing a multiple level or multiple layers of data redundancy. Got the point? Yeah, so we'll be having multiple level or multiple layers of data redundancy happening in this particular case. Now, when we have this thing going on, then what we should do is that we are actually out of this particular tension that what happens if one node goes down, because we already have that node's data copied at least twice, right?
Yeah.
So that also we don't need to think. We can just fire up a backup node and we just push that particular segment to that and along with some backup segments and then let the thing go on, right? That is one thing, and the processing becomes very fast. Processing becomes very fast because we are pulling out segments and asking them to work in parallel. So what I was telling is that this nodes and this partitions in each node and all the things that we are doing, and then we are putting that in that. So this is the main idea that takes into place when we talk about a map reduce algorithm. When we talk about a map reduce algorithm, the architecture that is going on behind it works like this. This is where the idea of HDFS starts. HDFS, the thing we got, the Hadoop file system. That Hadoop file system, the idea starts from this particular place. Thing number one about HDFS is that data redundancy. That is the first thing that they use to advertise about themselves. And the number two thing is that parallel processing. These two things are there that HDFS actually offers it. Okay. So when you're actually running your MapReduce algorithms and a lot of things, that it is actually what is happening behind. Okay. So this architecture needs to be understood because when you introduce Spark, you need to understand how it is differing from this one. So now let's dive a little bit more in depth. When we have got these segments of data and that are being given to the particular local hard disks of the nodes, and they once again being divided into multiple partitions to make sure that we are maintaining the data redundancy, we are actually helping ourselves from buying new hard disks. I mean, engaging new hard disks for putting the redundant data, which also used to be a very difficult thing in the earlier days of when Hadoop was not there and all those things, right? A lot of unstructured data, you need to buy new hard disks for your archival purposes and all those things. So that is also not being required when you're talking about this divide and put the redundancy in such a way that we are using the same hard disk, we are partitioning it, we are using the same computation power, but actually we are working on a particular segment of the hard disk, and all these things we are coming to the picture. So now, when you are dividing data, another thing that needs to be taken care of over here, and that comes into the picture, is formation of the sets. So now Hadoop did it in a particular way that it did not care about sets at all. I should say did not care about the structure of the sets at all. And what do I mean by that? So it will just start from the top. It will start breaking it into a particular a given size of segment, and it will start dumping the segments into the hard disk. That's the idea. So it is not really thinking about which way it can dump the structures so that dump the sets so that even if you are not really going through all the 10 million data you have, you can get a fairly close result. Why is this important to understand first? Say, for example, you are trying to pull out a data set from a stock market. And your idea is to go and find out that, okay, fine, basically prediction kind of a thing, trying to do. So now what happens is that now most of the people, most of the companies that are playing in the stock market, they actually keep this kind of data scientists for their kind of an idea. Like, so they'll be generating automated systems that will be automatically performing the stock buyings and sellings and all these things. Okay, depending upon the decisions. Okay. So why this particular thing is important that I was talking about right now, the formation of sets in such a way that even though you have not yet completed all the 10 million data that you have, the computation of the data, you can actually go and you can actually give some kind of a prediction. Why this is important? Say, in your stock market particular scenario that I'm talking about, you need this 10 million data to give a certain decision, but the thing is changing very rapidly. That can be a very practical scenario and a use case, right? The thing is changing very rapidly. So the number of data that is being dumped in your historical data set, that is increasing in a much more faster way than you can actually do the computations. So you never really go and finish your computation at all. You understand the problem? You are not
Yeah.
even going to finish your computation at all because it will
Because
just keep
you
on growing and keep on
keep
growing.
adding. Yeah. Yeah, you keep adding. Yeah.
It is keep on appending new data every
Yeah.
moment,
Yeah. Yeah.
right?
Yeah.
And the way you add new data in your data set, that is also controlled by a particular way of algorithm and all those things. It will just simply not pull every data. There is a particular uh, pattern on which it pulls data. But if the thing really goes very rapid, sometimes it might happen that you are going very fast. Even though you are going very fast, you are using some Intel Xeon processors and all those things, and like 100 GBs of RAMs and all those things. Still, you are running short in your computation power because the way the algorithm works is not giving you the entire full picture. I mean, it is just extending your cost. You are keeping on adding resources, you are keeping on adding nodes, but still you are kind of always falling short of things. You are increasing the thing, you cannot cope up after a certain period of time. You again increase the thing. So that is a particular point that has to be taken into consideration because you cannot keep on extending your resources infinitely. That costing cannot be involved. That you cannot involve that much of costing. So in this particular use case, this particular thing actually comes into the picture where we pull out the subsets in an intelligent order. Intelligently, we are pulling out the subsets so that we can actually know even beforehand. So what happens? See, every subset that you're pulling out, not necessarily one subset, maybe a mix and match of two subsets. So you have made out four subsets you have pulled out. Out of them, two in say subset number one and two together, and three and four together can give you an idea on the trend where the result is actually going to be. This is a little bit into machine learning part because, but I need to include this, otherwise I'll not be able to explain you the thing. So that is
But
some kind of, see, the assertions in this case, assertion, as I told you, expected and actual comparison. So the
yeah.
assertions in this case takes in form of extrapolation of graphs. We are diving a little bit into mathematics. I'll not go into the formulas and all those things, but just an
Yeah.
understanding. So let's say we are standing over here. So what do I mean by extrapolation of graphs? So for example, this thing is time, the x-axis, and the y-axis is some particular variable. Okay, along with time you are checking it out. So let's say the rate is coming from data set number one and two combined, like this. Okay, and let's take a green one that goes like this, something like this. Now, if I just try to join the dots a little bit, something like this, and if I try to join the red dots with the pink line, so now of course these points will be not considered, right? They are not really called errors, they are called outliers, right? So they are called outliers. So we are talking about outliers in this particular case, and we are actually getting rid of the outliers. So the way the extrapolation thing works is that, now let me take a black line. So for the green one, the extrapolation goes like this, something like this, right? And extends. So this part till where you have got the result. So till this point, it is interpolation. After that, it is extrapolation. And for the red one, that I will draw with a maybe blue line. For the red dots, interpolation, now extrapolation, it will go something like this. So the trends are kind of similar, right? The trends are kind of similar. So you're trying to pull out the trends. That is the idea. It is not that you're actually trying to pull out, I mean, the exact result. Of course, there's nothing called exact result, but you're trying to pull out the trends. So now the trends are going in a similar fashion. This kind of thing you can get if you're trying to pull out some data sets that have got some similarity with the original. Now, if you are not pulling out your data sets in an intelligent fashion, and let me try to take the black color as a, say, one data set, and it is giving you something like this, with this, and you have got another, let me take a yellow color, and that is giving you something like this. Then there is just no meaning of these two data sets. I mean, of course, meaning is there because at the end they will reach somewhere and you can find out the result because you'll be taking into account both of the results together. But at a given period of time, limited period of time, if you try to do an extrapolation and give a result, that will not work out because the first one will give you an extrapolated result of something like this, and the second one will give something like this. So they are going wide apart of each other, right? So that is what I mean when I talk about choosing the subsets intelligently. Because this is a very fundamental thing that comes into the picture when we talk about advanced data science and real data engineering. So now this lies into the generation of subsets, and this was another reason why Hadoop actually started losing its marketplace. So this is one point where Hadoop was falling short, and then comes the other one is that there's a particular issue that was coming with smaller files. When you talk about larger files, then of course this data sets is giving you a wrong idea, because it is not taking the subsets intelligently. So you need to wait for the entire thing to cover. I mean, complete first, right? And when you're talking about smaller files, a similar kind of issue came. Is that, for example, if you're talking about a very small amount of data, say you have got a very little, say you just have a data for last 1 week or something like that, and that is not a really big deal, really big data, and you need to work on that also. No, Hadoop fails in that particular case. Hadoop mainly works on this particular thing, right? HDFS, we know, right? Distributed file system, and it will be a lot of clustering of data. It will be putting them on those particular things, and then that kind of a thing. So it is not really a very suitable model to go for small amount of data, because just understand this thing. If you're trying to divide small amount of data in even smaller chunks, and then you're trying to maintain data redundancy and all those things, you are actually doing a lot of overhead, isn't it?
Yeah.
I mean this 128 MB of this default size that we have. Now, if your data is, for example, smaller than even 128 MB, what do you do? Right. So you need to go to the Hadoop configuration files, and then you need to make it reduced from 128 MB to something. Now, even if you reduce it, then still it is going for doing all those tasks, breaking the things, and once again storing them in multiple hard disks across multiple geographical locations, and then again running the algorithm on this particular pattern. So you are allowing a lot of overhead in this particular thing. So after that, Hadoop what they did, they introduced something called HAR. You heard about HAR? So HAR was a concept that Hadoop tried to bring into account to solve this problem. This HAR just means Hadoop archive. So what does a Hadoop archive do actually? And how was it solving the problem, and how did the problem yet not got solved? That is the point.
Okay.
So what happens in HR is that Hadoop archive was trying to do that, it was trying to take a lot of small files together and trying to put them together, and in the redundancy sets, instead of breaking one file in multiple smaller parts, it was taking multiple files and putting them in a redundancy set. It was trying to do a batch job processing kind of a thing, batch processing kind of a thing, and running a Mapreduce on that. Okay. So that is what HR was. But now again, the problem comes: what if you do not have multiple files to run your HR on? Right. So HR, I mean, HR was a very Apache itself released Spark. Okay, just to overcome the shortcomings of Hadoop. Right. So that was the thought process behind this. That okay, we can handle it like that, and until unless our Spark is ready, we can just give archive the HR architecture. And HR architecture, once again, it came out with a lot of documentation, lot of official release, and lot of things. So that bought them some time to work on Spark. This was one point. And after that, once Spark came into the picture, everything was changed. I mean, Apache, once again, Apache proved that Apache is Apache. That is the kind of thing. Anyway, so this is one thing. And number two is this slow processing speed, right? Because they are saying we're doing parallel processing a lot of things, but after all, Hadoop is slow. Hadoop is actually slow. In fact, when Apache first did this thing, they were running their advertising campaigns. Advertisers used to tell like 100x faster. I have seen 10x faster, 20x faster, but it itself told that Spark is 100x faster than MapReduce. I'll tell you what exactly is the architectural change they have made in Spark that made it 100 times faster. Okay. Also, this kind of thing, that this batch processing thing, right? As I told you, HR again, that was a batch processing technology that they tried to pull into account, right? Batch processing architecture was really failing, smaller, and then dividing it, and then we are actually introducing a lot of overhead, as I told you, which results into a lot of latency. So these were all related to one category of problem. that we are talking about latency, we are talking about breath processing, we are talking about this and that. So that comes one category of problems. Stupid division of subsets and no real smart works. The other division comes, there is absolutely zero support for real-time data processing. Hadoop cannot support real-time data processing. Absolutely not. Zero. Hadoop will only work on historical data. This historical data can be 1 year old, can be 1 hour old. Real-time scenario, real-time data processing, it has got absolute zero support, and which is terrible. So this was also another thing that they were really working on. And even if they gave us support for the small scale files and all those things, they were unable to give any support for this particular zero support for the real time, as I told. So for the real time, there was zero support they could have given. There was no release done of Hadoop that till date can even remote even being remotely close to handling this particular stuff. And another, last but not the least, that was the issue, that there are some security challenges they are facing. I mean, Hadoop, they made that so complex, that made this so complex, right? So a lot of authentications they wanted to include and all those things. So that actually was not really working out. So now, so we have got actually, if I list it down, we have got 3 points to talk about. Point number one being subsetting, and that takes into account the small file architecture and all those things, the breaking of the points, all those things. The number two thing we are talking about, the slowness observed, or the latency, or the overhead of time and all those things, basically time complexity. The third thing we're talking about is the real-time data processing. Now let's see how the Spark concept is coming into the picture as solving the issues. So now, what happens in RDD? See, RDD is the most fundamental data structure that is working under Spark. Okay. So it's really critical that you understand RDD. You really need to do it. RDD is basically an immutable data set. Immutable basically means that after it is born, it is not going to be changed. I mean, something is born, and in the entire life cycle, you are not going to be able to change it. So that is what an immutable thing actually means. So now this RDDs will be basically, see, each data set, what happens now, that you will be having multiple data sets in RDDs, right? So in the RDD format, all your data sets, they will be divided into some, you can say, what should I say? Some kind of a partition, not exactly what I was talking about earlier, this physical partition kind of a thing, not like that. That was a partition of the data set itself. And now I'm saying that each data set is, okay, fine. It is being a little bit problematic, I understand. Fine. Understand this thing. This one was the segmentation of the data set. Okay. When I was talking about this particular thing. Right. This was a segmentation of the data set. But when I'm talking about this in RTD format, what happens that each particular data set segment that you are working with, they can be, I mean, there can be multiple different categories of things going on inside that. Right? For example, it can have some, say, one RTD can contain a Python object inside that. Okay. It can have Scala. You heard about Scala, right? Scala is a very much used
Yeah,
technology,
I've heard about it.
language.
Yeah.
Have you ever worked on Scala?
No, I haven't.
Oh, fine, not an issue. Spark you can work on. I mean, Python. I think you can work on Java also. Java, I don't know how much it is used in big data, but Scala also is used. Anyway, so this RDD partitions are basically read only. Okay, so you are not going to be able to go and write something inside that because it is pulling out from the actual data sets, and it does not allow manipulation, and that is why it is immutable. Right. So they are read only. You don't have a writability on that. Now manipulation sometimes is required. I'll tell you why. I mean, why this point actually comes in the picture is that in some cases you will do some manipulations. Like for example, you are trying to do something like this. Let's say you are trying to calculate some kind of a calculation you're trying to perform, and each calculation depends on the previous calculated result. Okay. So, okay, I understand it's getting a little hard. Okay, let's understand in this way. So, for example, you know Fibonacci series, right? Fibonacci series, how it happens? 0, 1, 1, 2, 3, 5,
Three,
it goes like
5,
8,
8,
13,
13,
yeah, like that.
21.
So,
Yeah. Yeah.
every data, about leaving the first two, every data is depending on the data that is present before that, right? So 2 is dependent on the summation of the data that is before that. Right?
Yes.
3 is on this ones. 5 is on these two. So always n minus 1 and n minus 2. That will be the value of n, summation of these two. Right? So now, if that is the case, so this just, I wanted to give an example. I mean, when we talk about that data is dependent on the previously present data in the particular series. So when you talk about a data set, say for example, in a data set, it might happen that you have got, just forget about outliers. Let's say that we have got a very, we have got rid of the outliers. So now we have got a very, smooth kind of a data set, okay, where we can really work on. They are very much related to each other, kind of a thing, the data that you got. So now here, say for example, you are doing something like that we go to 1, 2, 3, and at the third interval, you need to sum the, or maybe say 1, 2, 3, 4, 5, 6, and 7, 8, 9, and you need to take each three groups and then sum the first elements of that. That should be the next first element of the next group. So 1 plus 4 plus 7 becomes 12. Okay. And 2 plus 5 plus 8 becomes, what is it?
15.
15. So like that it goes on, and next time it will take into consideration these three. So like that it goes on, something like that. So in this case, you are really adding up and you are trying to put in the values, because you
Yeah.
want to do the, say for example, these values are required for your extrapolation, this thing. You remember I told extrapolation.
Yeah.
you yeah, so for pulling out these values, maybe you need those things.
Yeah.
So that thing, if you're trying to write in the same dataset itself, that is not allowed in Spark, and that comes for the reason of data security.
Okay.
If it allows you to modify the data for your this data, I mean this purpose, extrapolation purpose, then it is actually you are manipulating and changing your data set itself, which should not be permitted. Why? Because you have got some redundant copies. This particular update will only take place on the local copy and not on the redundant copies. That will keep it there. I mean, that will make a situation where you have uh, so incoherence. There will be incoherence. So you don't want to have incoherence among your redundant data, because if there is incoherence, then your redundancy, the main idea behind redundancy, fails. It flops. Data security, incoherence, and inconsistency, you can say, all these things come into picture. So that is basically defying the actual idea of why we started to do data redundancy. That is the reason it is just allows you to do read only operations. And of course, if it is immutable, you understand that it must be a read only thing. So that is the, I just explained you the idea behind the immutability. How can I actually go and create RTDs? I mean, in real life situations. So what are the ways of creating an RTD? So once again, I'm repeating this thing. Understanding RTD is very, very critical. Okay, for understanding Spark. So I mean, this 5-hour workshop, you learn a lot of things. You have some questions that we shall take into account also. Maybe tomorrow when we sit, the first 10-20 minutes we shall be spending in questions if you have any. Okay, then we'll go into the later part of our workshop. But once again, just make sure that you understand that this workshop will not be a hardcore Spark tutorial. It is not going to be. So I'll set you on the path. Then you will be on the path from where you can just continue. So there is a particular concept called parallelizing. I'll not go into much details of this, but I'm giving you the points. Okay. And the other thing is called dataset referencing. So go and read these two topics. Remember these topics. Okay. They're just going to take you 5 minutes. That's it. Okay.
Yeah.
So what happens is this referencing part I'll still tell you a little bit. Parallelizing, you go and read the concept. In referencing of data set, what happens is that, for example, there is an external storage system, maybe your hard disk that you are using in the cluster, something like that. Okay, because when you're talking about clustering, right, most of the things you have to access remotely. because it will not be present in your local system. So that is what an external storage means, basically. In this case, external storage does not mean a USB hard drive, the way we tell it. Here, external storage means say a clustered hard disk that is not present in your local system. Okay, so it can be a shared file system, anything. HDFS also. HDFS is also basically on a shared file system only, clustering, right? Hadoop, if we talk about, right? So wherever you are getting this thing, I mean, any kind of a data source, you are referencing there, and you are we are pulling out the data in a particular formatted way, and then we are just placing in. That is what a referencing of a data set means, basically. Right. So Spark will be using this a lot, and this is done to achieve even a very much faster and efficient this thing MapReduce. I mean, than the actual MapReduce, because see, this data dividing and all these things, these concepts are actually uh, they came into the picture when you're talking about MapReduce. So they came into the picture when you're talking about MapReduce. This particular thing, segmentation. Spark uses segmentation. I just told that Spark uses an intelligent way of subsetting, right?
Yeah.
So yes, that is what we are talking about right now. So it uses an intelligent way of subsetting. It is not that it does not do it. So it is still in the Hadoop file format only. It is still in the Hadoop file format, but just in an intelligent way of doing the thing. So, and that intelligent way what you're talking about, right? That is the thing what RDD is, and that is how RDD does the job, right? And data sharing, and see, when we are working on a clustering, right, we need to do a lot of data sharing, because if you look at these particular things, they are actually doing a data sharing, isn't it? They have their own hard disk and all these things. This one you leave it. I mean, this one is just copying the entire data. Think about that model, but in this segmented way, right? So there is data sharing taking place because you need to copy the data over for making the redundancy come into picture. So data sharing is always happening. So this data sharing is extremely slow in MapReduce. And that is what makes it very, very, very difficult to work on MapReduce when you've got a large data set. Now, see, now are you understanding the bottleneck? MapReduce cannot work on a small system. And if the system starts becoming very large, MapReduce once again fails.
Yeah. So it's
So
like it only can just do like thoda, like neither too small, neither too big.
yeah, there is a threshold, higher and lower threshold points
Yeah.
to make MapReduce practically usable. Got the point? So
Yeah, I
make sure you understand the bottleneck. That is the problem. You cannot go too high because data sharing is too slow and the thing is just does not work out. Because and why data sharing is slow, I already told you, because there is this read write operation taking place between hard disk, because it is directly operating from hard disk. Right. Every time it is throwing to the RAM, then cache and CPU. So every single time this operation is happening. So lot of IO operations. IO means input output. IO operations is happening. Right.
Okay.
That that is how MapReduce is actually slow. The traditional MapReduce. And see, the why are you doing this redundancy? There is a particular term called fault tolerance. Okay. I mean, what I was telling, that is in the terminology, it is called fault tolerance. So one node goes down, you are just pulling out another node as a DR. DR means data recovery. So that is called fault tolerance. That is the idea. Now, if your fault tolerance itself, to give a fault tolerance architecture, the normal, now fault tolerance is needed, but this thing happens not very often, right? Seldom they will happen. It is not that every now and then your server is falling down. If it is happening, then you need to change your node. I mean, something is seriously wrong. But just to make sure that when that happens, it does not go wrong, every single transaction you are making much slower, which does not make much sense, isn't it?
Yeah.
Yes. So this one MapReduce, since it is giving you these parallel things and all these things and all this, so that is making the things terribly slow. In case of RDD format, what happens is that since see RDD still is using HDFS, because I told you, right? If you notice this thing, the file management system, it is still using Hadoop internally. It is still using HDFS, but it is doing a wonderful way of subsetting. The exact point we are trying to talk about over here. It is using a wonderful way of subsetting, and that is what RDD does, and that is what RDD is known for. Got the point?
Yeah.
Yes, exactly. So what are the points that it is, just getting rid of? It is getting rid of replication. It is getting rid of due to the replication across the hard disk. What it was doing, it was directly pushing in from the hard disk every single time. It is getting rid of that, which is known as disk I/O or disk operations, reading and writing, and also there is a particular thing that is called iterative way of doing the thing. And what is it?
Iterative.
Iterative. Iteration means repeating.
Yeah.
Iterative way of doing the thing means that it will constantly see cluster hard disk 1, cluster hard disk 2, and cluster hard disk 3. And they have their own individual RAMs where the main operation is taking place. Now, these three cluster hard disks are connected to each other. I mean, not directly. I am drawing a direct line, but they will be connected through the hub, not directly. Okay. So now, say they are connected to each other directly or indirectly, whatever it is. So there is a data sharing that is possible to be taken care of, right, among them. So, which is done in an iterative way. Means what? Means you have a segment, you just want to send that segment to another hard disk, maybe to the hard disk number 3. So they two are having a copy of the same segment. Let's call it, this is also one, and this is also one. And then there is once again the same segment. I mean, not the same segment. Let's say another segment, segment number 2, which is present over here. That comes over here, and yeah, I mean, we can just do a exact, because it is just 3 and 3 anyway. So we are doing something like that, 1 2 1 2 1 2. We are doing like this. So this thing is there now. This RAM operates on 2. This RAM is operating on 2 right now, and this RAM is operating on 1. You remember, right? These things are immutable in nature. You are not going and writing the new thing. So how are you doing it? You are. That is why I told you to learn about parallelizing. Okay. So when you learn about parallelizing, you know that how we can go and create new data sets over here. So that data set also needs to be sent over here for this replication thing, right? Since we are talking about real-time data processing also, oh my god. See, I am actually trying hard to keep these things uh, independent, but it is really difficult to keep these things independent of each other. They are kind of very related to each other. Right.
Okay.
So since we are talking about real-time data processing also, these particular segments that you are talking about, the data where you are storing, you cannot really say that I have got all the data, now I'm just giving it to you. That is not possible, right? So iterative way is there in which there is continual data redundancy we are trying to going on setup, right? So this is taking, see, just understand how it is separated. This thing is taking into place, taking place in the hard disk level. So of course, disk IO, all these things are involved, but that is internally happening. You are not really considering about that because your task of performing the operations, Mapreduce or whatever it is, not Mapreduce, I mean, whatever the algorithm you are running, that is being run from the RAM. Got how it is got, I mean, differentiated the two tasks. So this cluster, in the cluster, the redundancy of the data that you are trying to keep for
Yeah.
a safe storage of the data, that is taking that is being done in the hard disk levels. That is not really coming in the RAM levels, and the RAM is the one that is supplying the data to the processor to perform the processing. Got the point? So it is giving to processor, it is also giving to processor, and okay, and it is also giving to processor. But they are not really going, and hard disk is not really coming and indulging into this activity. RAM is neither going and indulging into this activity. So both the activities can be done together and in an iterative way. Got the point?
Yeah, I got it.
Yes. So that is what I wanted to tell you. So that is an iterative kind of an operation that is happening. Okay. So this is how our DD is actually doing the wonder that it is doing, and that is how it makes it 100 times faster. Okay, the particular thing that it talked about, right? That we are 100 times faster. It is 100 times faster than Hadoop. because of this particular reason. Because RAM can provide uh, a high IO rate, input output rate, and
Yeah.
we are completely sorry, a high read write rate, RW rate, and we are completely cutting down the IO operations with the database, right? That is one thing we are doing with the hard disk. That is one thing. Sorry, I'm just messing up the terminology, I think, sometimes. So it is just completely cutting out the communication with the hard disk, and it is only communicating with the hard disk whenever it needs a fresh segment within itself, or maybe there is a load balancing, I mean, sorry, fault tolerance thing that needs to be taken care right now because something has gone down. But that is also very rare. What the point?
Yeah.
So too much of data, na? Too much of stuff for one day.
Too much. Yeah. Yeah. Kind of like, yeah, it's reaching saturation now. Yeah.
Yeah, I understood. No, I'll just stop. I mean, there is no point because 7 minutes is there. I'll just stop. So now, just tell me if any particular point that you are feeling, or just do one thing. You've got 5 minutes of time, right? So mm, just try to give me an overview from your point of view, from your idea, whatever I've understood. So just try to give me a summary. Just try it out.
Okay. Okay. So let's start from like starting. Okay. When we spoke about Hadoop. Okay.
Yes.
Before that, because so before, okay, no, actually before that we spoke about RDM, Relation Database Management System. Okay, so we
Yes.
spoke about that, and so why, the structured data and how it works. So we did the whole thing with the client, unique key, primary key, and everything, and then we spoke about why. I mean, we told why Hadoop is important because of the unstructured of data and the data explosion,
Yes.
and so this whole the thing which is showing right now, we have a lot of data, and then the whole black box is
Correct.
there to reach the end objective. So then we spoke about all these things, okay, computing powers, which are your hardware, and your algorithms, which are your softwares,
Mhm.
and then from there we spoke about how the whole Hadoop ka filing system works. Like with your in your nodes, there are like, suppose a node has there are four nodes with like six things, it will be like 24 of them, and how you, like, data, how redundant, like how why redundancy is important. Yeah, this, we spoke all about this, but why redundancy is important, and then this whole thing about expites of data and everything. I mean, like the whole segmentation of the data. This all we spoke about. Then you told about the whole trends and everything, which was
Yes.
for um, trends and everything we spoke about before this one. And then also, sorry, then we spoke about the trends, and then the whole archive thing happened because, like, Hadoop, like this whole Mapreduce and everything was for like big data sets. But what if you have small data sets? The whole Hadoop started doing that, where they started compiling like small data sets into like one big one and tried to the redundancy, but it didn't really work out. So the
Yes.
whole archive thing kind of failed. And then we spoke about come down, yeah. Then we spoke about Spark, like, how Spark is not an extension of Hadoop, but those Spark does things internally with Hadoop, but then it is not a thing. Okay, it is like Hadoop. It's a file management system. Then we spoke about how, like, how the whole thing works with the cache, RAM, and with the hard drive. So the whole
Yes.
process with the CPU, cache, and RAM is pretty fast, but
Correct.
RAM to hard drive is pretty slow because like hard drive generally is very slow. And then the whole thing, okay, but RAM has like a volatile thing, because if anything happens, okay, and if the thing on the RAM will just go, but then uh, uh, that was, am I missing on to something? All right, and then the whole thing goes that way only, like, cache, RAM,
No.
hard drive, like that.
Yes.
Yeah.
You are not missing on anything. The thing is that it has been too much. I understand the